Hi, my name is Emily J. Hewitt, and today I'll be presenting my lab report for Lab 1, Constant Velocity, in one-dimensional motion. In this lab, I analyzed the motion of an object traveling with a constant speed along a straight line, using tracker software to get position and time data. I'll compare my experimental data with a computational model I built using Newton's second law, and discuss the results that indicate what the experiment and computational data are similar in essence. In this experiment, we will see the fundamentals behind a constant velocity, a zero net force, and compare the results of the observed and computational position data. The purpose of this lab was to investigate the motion of an object moving with a constant velocity in one dimension, and to understand the relationship between real-world observations and the theoretical principles of physics. In this experiment, I recorded a video of the can rolling along a straight path at a constant speed. I ensured the camera was stationary and focused on capturing the motion of the object across the screen. The motion was one-dimensional, meaning the object moved along the x-axis only. I then used Tracker to extract position and time data. To calibrate Tracker, I included a ruler with a known length in the video, which allowed me to set the scale for the scene. The system hears the can while the source is the push that I gave to the can. In this experiment, we assume that once in motion, the object continues with a constant velocity under the assumption of zero net force, which we will discuss further in a moment. Forces like friction, which could oppose the motion, are either negligible or balanced by an equal and opposite force. My experimental data was extracted using Tracker software. However, my computational data was derived using physics formulas. My initial position vector was derived from the first row of the table seen here. Because we are only interested in the x direction, I used the value of negative 3.28 to the 10 raised to the power of 3, or negative 3, as my x component. For my initial velocity, I extracted two data points and used the formula change in position over change in time. This resulted in an initial velocity of negative 0.363 in the x direction. Later on, we are asked to find the net force for this motion. Due to the nature of this lab and our knowledge of Newton's second law, we know that the net force will be zero. This can be proven with the equation seen here, change in momentum over change in time. Because the velocity is constant, there are no change in the momentum, making the net force always zero. The component cancels out in the kinematics equation for position, making our calculations even simpler. Another formula we'll reference later is the kinematics equation for position update. We embed this into our formula for our code to generate computational data for position update. Here we can see where I entered the initial conditions I described earlier into GlowScript. It was then important that I put in a working code that would generate the computational data based on my inputs. Here we coded the kinematics formula for position update into our input for ball position, since we knew that the velocity of this can remains constant, we simply put that velocity as ball velocity. Upon running this code, we generated two graphs that depict velocity versus time and position versus time, as well as actual data points used to generate these graphs. Here we can compare the results of my observations with predictions from the computational model. On the graph, the blue points represent the observed position versus time data extracted from Tracker, while the orange line represents the predicted position time based on the computational model. As you can see, both the observed and predicted data match closely, confirming my model is accurate and describes the motion of the object at a constant speed. The observed line is slightly less linear, but this could be attributed to human conditions. The can could have actually begun to slow down, which is to be expected as we are working in the real world with real conditions. However, it is clear that for the most part, the computational and observed data match closely. Now we address the question, what if we flip the axis? If I were to change the direction of the x-axis so that the positive and negative values were reversed, the object would still move in the same speed but in the opposite direction. The data would simply have an opposite sign for the position values. The overall motion and the relationship between the position and time would remain unchanged because the speed is constant, but the direction would be reversed. Another question asks, how many forces are acting on the object to result in zero net force? Since the object moves at the constant velocity, the forces on it must balance each other. For example, if there's a frictional force opposing the object's motion, there must be a force of equal magnitude pushing the object forward. In this lab, we assume that there are no other forces like air resistance or friction, so the net force remains zero. In conclusion, my analysis shows that the motion of the object was well modeled by the kinematics equation for position update, which is consistent with the principles of Newton's second law and for an object moving at a constant velocity. The comparison between the experimental data and the model confirms that the model is accurate. We also explored the effects of flipping the axis and considered the forces acting on the object, ensuring that the net force is zero as expected. Thank you so much for listening.